Hello and welcome back to another installment of the video series for BC Calculus for Mr. Billingham's class. I hope everyone is doing well. I will have more free responses for us to work on this week, as well as I will also put out the second part, the calculator required multiple choice questions for us to work on this week, and I'm continuing to go through chapter 10. I want you to remember from the previous video, we developed Taylor series for cosine and sine and e to the x, and here's what we got. I hope by now you're becoming familiar with the patterns in these and able to remember them. They'll be pretty useful to know for the AP exam. A little terminology right now. I can refer to these as either, for instance, in the top one, I can call it the Taylor series for sine of x centered at x equals 0, or I can call it the Maclaurin series for sine of x, which means exactly the same thing. Maclaurin series are always centered at 0, whereas Taylor series can be centered anywhere. If I include all of the terms for sine of x centered at 0 up to the 5th degree, for instance, let's take a look at that, then this is no longer a Taylor series. It's now a Taylor polynomial, or a Maclaurin polynomial. And I can call it a Maclaurin polynomial for sine of 5th degree, but I can also talk about its order. Order is an interesting concept. It means how many terms we actually calculated what the coefficients are. And with this one, it could be a 5th order, or because as we know the coefficient of x to the 6th is 0, it could also be 6th order. It's really impossible to tell, so it could be either. I hope that makes sense. I might have stopped calculating at the 5th degree term, in which case it would be 5th order, but I also could have gone out and calculated and realized the coefficient of x to the 6th was 0, so I really am including the 6th degree term. It just has a coefficient of 0 and doesn't show. So it is a 5th degree polynomial, but a 5th or 6th order polynomial. Let's practice making a new Taylor polynomial from one of the ones we already have. This is a very useful skill. We don't want to have to build a Taylor series for cos 2x from scratch. We want to do it instead by starting with our knowledge of the Taylor series for cosine of x and substituting 2x in for x. I'll do the math here. I'm stopping with a 4th degree term because I realize that that will wind up still being a 4th degree term after I've substituted 2x for x, and they do want a 4th order polynomial. And here, after substituting, expanding out, and canceling terms, we find our answer. The 4th order Taylor polynomial approximating cos 2x near x equals 0 is 1 minus 2x squared plus 2/3 x to the 4th. I think it's time we looked at a Taylor series that is centered somewhere else besides 0. First, I'm going to put out the general formula for a Taylor series centered at a instead of 0. Notice the difference between this and the previous Taylor series centered at 0. Instead of f of 0, f prime of 0, we have f of a, f prime of a, and instead of all of the variable parts being x, x squared, x cubed, now they're x minus a squared, etc. But the general formula is pretty much the same. Let's use this formula to figure out a Taylor series for e to the x at x equals 2. Since every derivative of e to the x is e to the x, every f of 2, f prime of 2, f double prime of 2, all of those derivatives will all be e squared. So the Taylor polynomial is going to look like this. If you were to graph both this and the Taylor series for e to the x centered at 0, ultimately the two graphs would be identical. However, they would start converging first at their respective centers. So the Taylor series for e to the x, which is 1 plus x squared over 2 factorial plus dot dot dot, would start by being most accurate near 0, and the convergence would spread out from there, whereas the graph of this, if you were to do it in Desmos, would start off being most accurate near 2. Let's take a look at that graph. Here on the left, we have the Taylor series for e to the x centered at 0. And notice that the red graph is the e to the x, and the blue is the Taylor series for, I think I stopped at 4. Let's see, that would be 7th degree Taylor series in the blue graph. Notice it's converging most rapidly near 0. Now compare that to the next graph, which is the Taylor series for e to the x, but this time centered at x equals 2. I think it's pretty obvious that in this one, the convergence is starting not at 0 anymore. In fact, it's not even converging that well at 0, but the convergence here is starting at x equals 2. Again, it's a good time to remind you that e to the x, sine of x, and cosine of x Taylor series all ultimately converge for the whole real number line. So both of these would ultimately have exactly the same graph if I didn't stop at a 7th degree polynomial, but went out to infinity and got the complete graph. In the next problem we're going to look at, we're going to take a 3rd degree polynomial and then write 2 Taylor polynomials for it. One centered at 0 and the other centered at 1. You might remember this was going to be a problem that I planned to put on the chapter test, but it looks like we may not have a chapter test, although I'd like to hear some feedback from you guys on that. Under some sort of an honor system, perhaps, might you like to take a chapter test if you knew it couldn't hurt your grades? Let me know. All right, so here's the problem. So we want to find a 3rd order Taylor polynomial for 2x cubed minus 3x squared plus 4x minus 5, centered both at 0, and a second one centered at 1. To do this, I'm going to need to take f prime, f double prime, and f triple prime and evaluate each of those at both 0 and 1. So here's the math behind that. Finding the first 3 derivatives shouldn't be that hard. Now let's evaluate these at 0. Shouldn't have been too hard to substitute 0 into each. After all, you just get the constants, and that should be enough information for us to write our 3rd order Taylor polynomial for the original polynomial centered at x equals 0. I'll write it out now, and you should be able to follow this pretty easily. Notice we got the original polynomial right back, but this time in ascending order instead of descending. Of course, that should be no surprise. To figure out the Taylor's polynomial for this function at x equals 1, we're going to need to evaluate the derivatives at 1. That really wasn't very hard either. So let's go ahead and write out the 3rd order Taylor polynomial for the original polynomial f centered at x equals 1. There's the pattern we have to follow. If I plug numbers in, I can see that f of 1 is negative 2. F prime of 1 is 4. F double prime of 1 is 2. So, sorry, there's a mistake there. F double prime of 1 is actually 6. So that would be plus 6 x minus 1 squared over 2 factorial, and then finally plus 12 x minus 1 cubed over 3 factorial. And that simplifies to be negative 2 plus 4 times x minus 1 plus 3 x minus 1 squared plus 2 x minus 1 cubed. Now, it's not at all obvious that that's equal to the original function, but if you graph both this and my earlier p of x in Desmos, you will see that the graphs coincide perfectly. I'd like to look at one more example of getting a Taylor series from an existing Taylor series. This is certainly the way you want to do it on the AP exam, rather than going through the figure out all the derivatives from scratch approach. So here's our problem. I'm going to do this in a sequence of small steps. First, I'm going to start off with the Taylor series for e to the x. Then I'm going to substitute 2x in for x, subtract 1 from the result, and divide the whole thing by 3. All right, start off with e to the x. Now I'm going to substitute 2x in for x. I didn't bother to do any simplifications early on because after all this is an infinite polynomial. Where would I stop? So now I'm going to subtract 1 from everything. In general, I like to show at least the first 3 terms and then a generic term, which is what I've done here. Finally, we need to divide everything through by 3. So the moral of the story is don't reinvent the wheel. If you know a Taylor series for e to the x, you can do substitutions, subtractions, divisions, etc. to get a Taylor series for e to the 2x minus 1. Also, for the AP, you do not have to simplify the answers. You can leave them without factoring, canceling, etc. I have one last problem that I want to show you that I think is really cool, and this is as good a time to show it as ever. I'm about to prove something called Euler's formula. I think it's really cool, and it's neat that you've gotten to a place in mathematics where we can do this. So try to follow along. I'm going to start by writing out the formula for e to the x, the Taylor series formula for it, centered at 0, and I'm going to use the 8th order one, just so you can see enough terms that the pattern really emerges. So there they are, the 8th order, and I put plus dot dot dot, but I'm showing the first 8 degrees. This is really an infinite series. I'm not stopping at a polynomial. Now I'm going to do something a little weird. We've really been just dealing with real numbered functions, real valued functions this year, but I'm going to substitute ix in for x and simplify a little bit. So that's after substituting ix in for x. Now you might remember that I is kind of a cyclical thing when you take it in powers. It goes I, negative 1, negative I, 1, I, negative 1, negative I, 1, and so on and on and so on and so on. So I to the 4th and I to the 8th are both equal to 1, and I to the 5th are both I, etc. So let's make those substitutions now. Now I'm going to rewrite this. First I'm going to put all the terms that don't have I in, and I'll group those together, and then I will have all the terms that do have I in, and I'll put all those together and factor the I out. Now if you look at these little collections of terms inside the parentheses, you should notice what they are. The one on the left is the Taylor series centered at 0 for cosine of x, and the one on the right after the I is the Maclaurin series for sine of x, or the Taylor series for sine of x centered at 0. So let's rewrite with this in mind. So weirdly enough, e to the ix is cosine x plus I sine of x. To make it even more clear, let's substitute pi in for x. Now we know cosine of pi is negative 1, and sine of pi is 0, so we get e to the I pi is negative 1 plus 0, or if we want, e to the I pi plus 1 equals 0. And this is really cool because it takes the 5 most important constants in mathematics, 0, 1, I, pi, and e, and has them all connected in a single equation. I think that is pretty darn cool. So anyway, that's the end of this video lecture. I hope you found it enjoyable. I hope you're all staying safe and healthy. And I wish I could see you. I hope I get to see you before you go off to college. I hope the future gets brighter. Anyway, stay in touch. Bye-bye.